n, I'm missing just one thing, plus c, and that will take care of all of the possible answers. And this rule right here has a name. This formula has a name. This is called the power rule for antiderivatives. This rule is awesome, you know, because it works for basically every power of x that you could ever think of except one. There's one power of x where this formula would break down. And you can see it right here. Think about a value of n that I could possibly plug in right there that would cause a problem. Negative 1, right? If n is negative 1, this is undefined. Do y'all see that? So I'm going to just say here, down at the bottom here, this is the power rule. This works if n is not equal to negative 1. So as long as the n right here, as long as that n is not negative 1, this formula will work. Right? That n right there. So what if it is negative 1? Do we just give up? Do we just surrender? Yes, we surrender. Let's go. Have a good day, everyone. No, what do? We take a look at that case, okay? Let's take a look at that case. If n is negative 1, then this becomes x to the negative 1 as our original function. And we need to recognize that function as being 1 over x, right? And then we ask ourselves from Cal 1, what do you take derivative of to get that? The natural log, right? So you hopefully remember learning this in Cal 1 that if you take the derivative of natural log of x, you get 1 over x. So derivative of natural log of x is 1 over x. So that we just have to know. Now there's one thing here that I'm going to state that may not have been stated in Cal 1 when we were taking derivatives, is that when you're talking about antiderivatives, the antiderivative of this is natural log. What we will do here is we will put the absolute value of x. Now let me explain why. And this might be a little bit tricky, but I'll try. So imagine that you're in Cal 1, right? And you're given this function, natural log of x. And you're asked to find the derivative, right? We would all say what? The derivative of that is 1 over x, right? All right, go back up here. What's the domain of this function right here? What can you not plug into a natural log? Negative, right? Let's see. So the domain of this, the domain of the f function here is, yeah, you just have to make sure that you're plugging in numbers that are greater than 0. Okay, you can't plug in 0, can't plug in negative. So the domain of that function is 0 to infinity. All right? So if you're going to look at this function and graph it, if you graph that function, it only exists to the right of the y-axis. And if we go look at its derivative, where does the derivative exist? What's the domain of this? Everything except 0. So do y'all see that the domain of the derivative is actually more than this? Yes? So back in Cal 1, when we were doing like where is a function going up and down, increasing, decreasing, that sort of thing, what you would do if you were asked to look at this derivative is you would only look at it on this domain. You'd only be looking at this here because that's the domain of the original function. Over here, it's different. If I start here, right? If I start here, what's the domain of this function? Everything except 0, right? But if you don't put the absolute value here, what's the domain of your antiderivative? You have to be greater than 0, right? So the domain here is restricted more than the domain there. So in order to open up the domain and make it match this domain, we put the absolute value here. So you don't need to, like, that's not critical that you understand everything I just said. We just need absolute value there, all right? I'm just trying to explain why. It's so that the domain of our antiderivative matches the domain of the original function as opposed to losing domain. All right, so that's our power rule, and that's the special case. So in most textbooks, you'll have this final version of the power rule. And I'm going to put it off camera. I'm going to put it over here just so we have it. So power rule. is this. If f of x equals x to the nth power, then the antiderivative, capital F of x, will be equal to one of two things. It'll be 1 over n plus 1, x to the n plus 1 plus c, if the n is not equal to negative 1, and it will be natural log of the absolute value of x plus c if n is equal to negative 1. So it's like your two different scenarios. Okay? So now that we're doing this, had you done this? No? Okay. All right, let's do something a little more complicated. So I want you to find the antiderivative of this one. So we'll start with this. This is not going to be that much more complicated. How about that? That plus that. So the reason I'm putting this example up first, right, as our first more complicated one, is the natural question here is, if you're trying to find the antiderivative of a function, and you have three terms, right? Additions or subtractions, you have three terms. Do you think that you can find the antiderivative of them individually? What do you think? What does your gut tell you? Can you do it individually? What do you feel? Yes? So back in derivatives, right? When we were taking derivatives, when you take derivatives, if you have sums, like sum and addition, can you take derivatives individually? Yes, with sums, with plus and minus, right? With addition and subtraction, you can take derivative of each term separately. Well, the good news is that it works exactly the same way with the antiderivative. You can do the antiderivative of each one separately. So I can go capital F of x equals, okay, what do I take the derivative of to get this? X squared. We did that one already, right? X squared. Okay, plus. Now this one we have not done, and we have two options on how to do it. I put that one up there intentionally because I felt that you would probably be able to look at it and just see it. Do you all see it? Without even using this rule. How many of you, just show of hands, how many of you just see what the antiderivative of that is? Okay, so about half, a little more than half. What do you take derivative of to get this? X cubed, right? Just x cubed. Because what would the derivative of this be? 3 comes out, x reduce the power by 1, right? X cubed. Plus, okay, the antiderivative of a constant, right? Antiderivative of a constant is just the constant times the variable x. So again, think about it. What's the derivative of 4x? 4. Because the derivative of x is 1. Right? So it would just turn into 1. The 4 comes for the ride. I'm missing something. Plus c. All right, so the only purpose of this problem was, again, to show that you just think about each one of them individually. Also, we want to be able to recognize things. Now I'm going to give you one where we're going to probably have to use the formula. All right? So what about this? What's the antiderivative of this? All right, so you're probably not going to just look at that and know the answer. But we do have this rule, right, that allows us to take the antiderivative of x to any power, right? Any power. So what we're going to do first is we're going to rewrite this function as x to a power. Instead of using what kind of notation? What kind of notation is this called? Radical notation? Or roots, radical. Radical notation, we're going to convert it to the other notation we use, which is called rational exponents. Right? So we're going to go from one to the other. So the other way I can write this is x to the what? 2/3. 2/3. I'm using that property that the nth root of x to the m equals x to the m over n. That's a property from college algebra. I actually went over that in class last week with my class. Right? That is property of exponents, so that's what I'm using here. And that's just so I can get it to x to the n, right? And now, I just go play that game, right? And I'm going to go a little more formally through this. Capital F of x should be, all right, let's look at the formula. The n we have is not -1, right? It's not -1. It's what, 2/3? So it's not -1. So I'm just going to plug everything into this formula. It's going to be 1 over 2/3 plus 1, x to the 2/3 plus 1 plus c. And then I just need to like figure out what all those numbers are. You remember in Cal 1 when you were doing derivatives and you were using the power rule and subtracting 1, you had to kind of get used to subtracting 1 from fractions. In Cal 2, you have to get used to adding 1 to fractions, just because you have to do it a lot. So what's 2/3 plus 1? 5/3, right? Everyone here is going to be a different place with that. But 2/3 plus 1, get a common denominator, right? 2/3 plus 3/3, 5/3. Okay, so let me continue. I have 1 over 5/3. X to the 2/3 plus 1 is 5/3 plus c. And what's 1 over 5/3? 3/5. The reciprocal, right? That just reciprocates. So we have 3/5 x to the 5/3 plus c. That's it. You can check your work, can't you? Can't you check this answer? That's one of the beautiful things in Cal 2. I don't think it's beautiful. It's just one of the good things. Right? Is you can check your answer, right? How do I check that this is correct? Take the derivative. So if I ask you to take derivative of this, the 5/3 would come out and get killed off by the 3/5, right? They're reciprocals. That would become a 1. Then I'd do x to the, I'd subtract 1 from that. 5/3 take away 1 would be 2/3. And so you get back the original. And of course, the derivative of c is 0. All right? Any questions? Okay, how about this one? Why don't I give you a minute or 2 or 3 to see if you can figure out this one. I want everyone to get me an answer. All right, I want you to tell me what is the antiderivative of 4 square root of x minus 3 over the cube root of x plus 9 over x to the 5th. So I'll give you a hint. There's 3 terms, right? So you're going to look at each one individually, right? Each one individually. That's the first hint. For each one of them, you're going to try and write each term to have an x to a power. And that needs to be x to a power on top. It can't be x to a power on the bottom. It needs to be moved up to the top. And then you're going to apply your power rule, all right? Work together. If you're having trouble, talk to your neighbor, see if they're having the same issues you're having. And give you some time, yeah? Well, how's it going? How many of you feel like you got some? Struggling? Anyone struggling?
I know I'm on the right track.
I'm going to start working a little bit of it and see how you're doing. So what I've written on the board here, I have done no actual calculus yet, right? All I'm doing is rewriting everything. Rewriting this as x to the half, rewriting this bottom as x to the 1/3, that's using this right here. And then this one, I decided to bring this one up as a negative exponent now. On the next line, I just brought this one up, negative exponent. And the reason I'm doing that is because this rule only applies if the x is in the numerator. If the x is in the denominator, it doesn't work. So that's just me getting every single term to be a constant with x to a power. Constant, x to a power. Constant, x to a power. And now what I do is I try and find the antiderivative of each one. Any questions on that step? Okay. Now, how do we deal with the constants out front? What do you think? What's that? So they're just going to come along, just like when you did derivatives, right? When you take a derivative, if you had a constant out in front of the function, it would just come along with you, right? I'm going to do the same thing. I'm kind of going to ignore that. Let me do it right here. I'm ready for the antiderivative now, so I'm going to write capital F of x. So here we go. Capital F of x equals... All right, the 4 is going to come for the ride, and now I'm going to apply the power rule to that piece right there. I'm going to use the power rule right here. My n is 1/2, so it's going to become 1 over 1/2 plus 1, x to the 1/2 plus 1. Now, I should put plus c, right? But I'm going to do a plus c here, a plus c here, a plus c here. Each one of these individually would have a plus c. And if you add 3 constants together, you get a constant. So what I'm going to do is at the very end of everything, I'm going to put plus c just once. And that will cover all of them. All right, so now minus 3. And then I have the 1 over what? If I'm using the formula, 1 over negative 1/3 plus 1, x to the negative 1/3 plus 1. Then I would have a constant again, and then plus 9 comes for the ride, and then 1 over the power is negative 5, so negative 5 plus 1, x to the negative 5 plus 1, and then my plus c. Then my plus c. Yeah? Now, you don't have to write all that down. If you can do all that arithmetic in your head, that's fine. This is the beginning of this, so I just want to make sure I have every little detail up there. Okay, so this is now 4, let's see, what's 1/2 plus 1? 3/2. What's 1 over 3/2? 2/3. Then this is x to the 3/2. And then minus, let's see, 3, and then times negative 1/3 plus 1 is 2/3. 1 over 2/3 is 3/2, and then x to the, this we already said that was 2/3. And then plus 9 times 1 over, okay, this is just negative 4. 1 over negative 4, can't really do anything with that. And then x to the negative 4 plus c. Any questions? Clean it up. There's a little bit more arithmetic to do here. Put these together. That's 8/3. X to the 3/2. This is 9/2, x to the 2/3. And then this is going to become a minus because you're going to put those two together. It's going to be a negative number. So it's minus 9/4 x to the negative 4 plus c, and that should be my antiderivative, my general antiderivative. Okay? All right with that? Okay. All right, we're gonna, yes?
So on like tests and exams, do you want us to keep it in that form, or do you want us to like drop the exponent?
Good question. So I know back in algebra, they'll say like, don't ever leave a negative exponent, like always drop it down, things like that. In calculus, nah, it doesn't, because we might need to do the antiderivative again. So then we'd have to move it back up and do the power rule. So just leave it like this. All right, let's do another one. How about this? One minus 3x plus the cube root of x to the fourth, all of it over x squared. So I think we've already established that when you're taking derivatives, or sorry, when you're finding antiderivatives, that if you have multiple terms, you can do them individually, right? What we have not established is how you handle a quotient, right? If you have two things being divided, like we do here. So in Cal 1, if you had two things being divided and you were doing a derivative, was it just the derivative of top and bottom separately? No, it was the what? The quotient rule, right? So things weren't good in Cal 1 when it came to quotients, and that means in Cal 2 it's also the same. There is no easy way to just do the antiderivative of top and bottom separately, all right? So there's no way we can just treat the top and bottom independent from each other and doing antiderivative. So you sit there and you go, okay, well, is there a rule? Is there a quotient rule for antiderivatives, right? And the answer is no, there is not. So for this problem, there's no way for us to go backwards unless there's some way that we can rewrite it as x to a power plus or minus x to a power plus or minus x to a power plus or minus x to a power. If we can't do that, we're stuck. Can we? We can, how? Exactly. Because there's a single term in the denominator and multiple terms in the numerator, you can split this into three separate fractions, right? I can do this over this, this over this, this over this. That I can do, right? And then maybe from there I'll be able to attack each one. So let's start with that. So that's just an algebra move, right? 1 over x squared minus 3x over x squared plus cube root of x to the fourth. You know what? I'm not going to do that. I'm going to write x to what power up top? What's that? 4/3 all over x squared. That's just algebra, right? That's the reverse. That's reversing addition of fractions, right? You can add fractions together if they have the same denominator. So if we put these together, it would give us this, right? So we're just undoing that. Now, each of those, can we rewrite each of those as x to powers? Let's see. The first one can be rewritten as x to the -2. That's just bringing that up. This one is the curious one. I put this one here intentionally. What happens to the x's here? One of these goes away and that one's gone, right? Which leaves you what? 3 over x? We can bring that x up, can't we? Yes? But what would happen if we bring it up? It would be x to what power? -1. And that was the special case, right? That was the special case. If n is -1, we're going to have a natural log. You see that? So instead of bringing it up, this is what I'm going to do. I'm intentionally leaving this as 1 over x because I know the antiderivative of this is the natural log of the absolute value of x. I'm recognizing it's the special case now. This one is not the special case, right? Because here, this is not x to the first power, it's x squared. It only works if it's 1 over x to the first power. And what about this one? How do I clean this up? Yeah, so you're taking this power and subtracting that power, right? You're doing 4/3, you're taking away 2, which is the same as 4/3 minus 6/3, right, which is negative 2/3. So x to the negative 2/3. Right, that's again just a property of exponents from college algebra. Any questions? We have rewritten each, well, we split it up, and then we rewrote each one of these as x to a power, except the middle one, because we recognize that it's going to be the special case. And now I'm ready to apply the power rule. So here it is. How are we doing on time? 40 minutes? Okay. So power rule, here we go. I'm going to do this one first. It's going to be 1 over negative 2 plus 1, x to the negative 2 plus 1, and then minus 3. That comes for the ride. And now I'm just going to use what I know about this. The antiderivative of this is natural log absolute value of x. Natural log of the absolute value of x. And then plus, now the antiderivative of this, which would be 1 over the power, negative 2/3, plus 1, x to the negative 2/3 plus 1 plus c. Is my pace okay on this? Are y'all all right with this? Yeah? What's this turn out to be? Negative 1. So this is just negative x to the negative 1. That's what that is. And then this one is just minus 3 natural log x, or natural log absolute value x. And let me see. Put those together. I get 1/3 when I put those together. And then 1 over 1/3 is 3. So I get plus 3 x to the 1/3 plus c. We could check our answer, couldn't we? I'm not going to, but we could, right? Just take the derivative, and when you take derivative, we better get back this line right here, right? All right, y'all feeling all right about this? Okay, we're gonna do one more quick application, and then I'm gonna move into the next section. All right, we're gonna actually move into the next idea. So, one of the things that we wanna be able to do here is use this idea of an antiderivative to solve a problem like this. So just remember that the antiderivative is just you going backwards from a function. You're going backwards to where, you know, what function can you find that when you take derivative of that you get the one you started with, right? So imagine you're in Cal 1 right now, right? And I give you this. If f double prime of x equals, let's go with 12x, all right? So I'm telling you right now that the second derivative of a function is 12x, right? I'm giving that to you. And I'm telling you that the first derivative of this function evaluated at 1 equals 6, and the original function evaluated at 2 equals 4. The question for you is, find the original function f of x. All right. So I just want to kind of draw a picture first of what's happening. So we have some function f here, right? There's the graph of f. I don't even know what it looks like, right? There's the graph. That's some function f. That would be the one we're trying to find, okay? I don't know what that is, right? So this is the one. We want to know what this function is. In Cal 1, we could take the derivative of that function, right? We could differentiate that function, take the derivative, and we would get a new function that would have, most of the time it would be a different graph, right? That would be a different graph, but that would be our derivative. And then there's nothing stopping us from taking the derivative again, right? Take the derivative again, And that would give us the second derivative, and that function is this one, right? And I'm telling you that that function, that second derivative, is the function 12x, which is a linear function, right? So I'm giving you this, right? And I'm asking you to give me that function. You'll see it visually? But I've given you two other pieces of information. And this is the part I really want you to see. These two things are important in the problem because if we're going to start here, right? If we're going to start here and try and get back to that one, what do you think I'm going to do to go from here to here? The antiderivative, right? The antiderivative. But what do we get every time we do an antiderivative? Plus c, right? And so if I try and go from here to here, I'm going to get a family of functions, aren't I? They're all going to have the same sort of shape to them, right? They're all going to be vertical shifts of one another. And the antiderivative, I don't know which one it is, do I? I don't, right? I don't know which one of these it is. However, I tell you something, right? What do I tell you? The derivative, right? The first derivative at 1 is 6. Well, here's your first derivative. If you go to the value 1, you should have